Hello, students. Another topic that we're going to find very useful as we navigate Calculus 2 is the theorem entitled L'Hopital's rule. Now, one of the Bernoulli brothers actually devised this particular technique, and L'Hopital, who was basically credited with devising the first calculus text, actually credited the Bernoulli brother for this work in his first calculus text. However, the name L'Hopital has been tied to this result. It's not Bernoulli's rule, it's L'Hopital's rule. So history has a way of manufacturing, some accolades that weren't intended. I certainly credit L'Hopital for being very upstanding about declaring the work from the Bernoulli brother, but be that as it may, we will talk about this result as L'Hopital's rule. So what do we mean when we say L'Hopital's rule? Why, when we think about it, is it something that has to do with limits? And if it is, we already know how to compute limits. We learned many techniques in Calculus 1 that gave us very, very good techniques, usually meaning a lot of algebra, but how did we find that we were any good at limits? It was a matter of understanding the indeterminate form. Just like when we studied derivatives, we saw the basic definition of the derivative was indeterminate form. If we had indeterminate form in our limits, we couldn't say anything about the limit. We would need some type of algebraic manipulation. If we had a function with a hole in it, we had to do something in addition to declare the existence or non-existence of the limit. And so what we're going to find out with L'Hopital's rule is that this adds an additional tool to computing limits. And you might think about this and say, this could have been very useful in Calculus 1. But as I say many times, the techniques that you learn in Calculus 1 are indispensable. And having more techniques to solve problems is actually better, because you may find as you navigate more calculus and more engineering mathematics or STEM mathematics that having additional ways to work a limit or to devise a solution is much more valuable than just basically having to reside with a singular technique. So what I want to do is just give you some background information as to how we can set up this process. So I'll share my screen. Now, you will have opportunities to work with your lecture notes that you have online, but basically I want to go through some of the definitions in theory that we'll need to do. Understand that the foundation of this is very important, but as you work through physics, as you work through calculus, and as you work through engineering math and others, the technique of computing limits by L'Hopital's rule will be very, very important. So think we've just pretty much transported ourselves back to Calculus 1. So just to remind you, the indeterminate forms that will be covered by the theorem will be the ones that we're already very familiar with. That is, the indeterminate form 0 over 0 and the indeterminate form infinity over infinity. Now, just to play devil's advocate, these aren't the only indeterminate forms that we will see, and we'll do some examples of these, but I want you to be very flexible as you work through these problems. Take advantage of this new technique and don't be afraid of it. So other forms that we will find that will not allow us to directly compute a limit will be the following ones. And I've referred to these before. one of the ones, the last one here is a famous one, infinity minus infinity. We know infinity plus infinity gives us an infinite result. That's determined. But infinity is not a number. So we can't say that these absorb each other. We don't get zero. Maybe we could, but it certainly wouldn't be because we did that computation, which doesn't even exist. No pun intended. Some other forms that do not give us a determined conclusion will be 0 raised to the 0, infinity raised to the 0, 1 raised to the infinity. I mean, we really don't know what that is. I mean, if something is close to 1 and the power is becoming infinite, we don't know. We do not know. And of course, one that just bugs every calculus student is 0 times infinity. Just like looking down at the last one, that is not 0 necessarily. And that would certainly not be a conclusion that we could make based on just observing that condition. Now, you might be thinking, how is this theorem going to allow us to work with these? Well, the algebraic manipulation that must occur is that these forms must be converted to one of these two. That is, the theorem will address 0 over 0 and infinity over infinity. And there will be algebraic techniques and also uses of continuity with logarithms that will allow us to convert these forms into one of these forms. And that's the key. So just remember, if you apply Hopital's rule, just before I've even stated it, these conditions, one of these would have to be met. And without it, it would be moving forward blindly and would be an invalid use of the theorem. We just know in calculus that as we move forward and we're applying the mean value theorem, we're applying the chain rule, whatever theorem we have, we must make sure that the hypotheses are satisfied. Otherwise, our result is invalid. Now, I want to just quickly go over some rudimentary foundational theory, just so you can feel comfortable with this. And of course, in the lecture notes, there is a more detailed representation of Hopital's rule, but I want to provide you some very straightforward results that will give you a little bit more confidence. Now, the first result is the extended mean value theorem. Now, why do we call it extended? If you notice here, we've got more stuff. Normally, what we're interested in or what we're used to is f prime of c, and we have f of b minus f of a divided by b minus a. Well, you see the existence of another function g. So what we have done is we have extended the first result, and it's called EMVT, for extended mean value theorem. Now, again, hypotheses are very similar to what we saw before. We would need that f and g are differentiable on an open set, a to b, this open interval, and also continuous on the closed set. So we need continuity at endpoints. Now, one thing, you're looking at this and saying, well, this needs to be defined. We certainly would be in trouble if it weren't. So what's going to get us out of that is requiring that g prime of x be non-zero on the open set. What that's going to tell you is that you have an invertible function g. Therefore, the g of b minus the g of a would never be 0. And of course, g prime of c would never be 0. So this requirement will be needed in order to state this as a result. Okay, so again, remember, the interval can vary, but the a and b are fixed. So when we discuss this and you're working with mathematics, especially in calculus, when you're working with limits, you often fix an interval about a particular number to make your estimations easier. So this is the same thing, just like we did before with the first mean value theorem. Now, I just want to summarize the proof, which you know uses Rawls' theorem. And it's not difficult. And so if you want to spend more time with this, feel free to do this. It's a very straightforward result. You might go back to your Calculus 1 notes and review that proof because it's basically the same. So what we want to do in order to validate what's in the red box here is to apply Rawls' theorem to a function that will get us to the finish line. And that function we're going to define to be h of x, which will be f of x minus f of a, minus this number times g of x minus g of a. That is f of b minus f of a divided by g of b minus g of a is just a number. So this is a coefficient of g of x minus g of a. Now, just like we did before, we have manufactured h to have nice properties. Since f has continuity and g has continuity on the closed set by the algebraic properties of continuous functions, h is also continuous there. That is, algebraic combinations of continuous functions are continuous. Same for differentiability. So h would also be differentiable on the open set as we have here because both f and g are differentiable there. So that's a freebie. We love freebies. Now, of course, if we're going to apply Rawls' theorem, we just take the derivative of this, which is very simple. H prime will just be f prime of x minus the number f of b minus f of a divided by g of b minus g of a times g prime of x. And so let's just recall, how do we validate Rawls' theorem? Well, we need that the function evaluated at the endpoints would coincide in value, okay? And we need the differentiability and we need the continuity, which we already have. And once we have that, then we have the existence of at least one horizontal tangent. So the only thing that's left is just verifying that the endpoints give us the same value. And it's very simple. So now you're thinking, well, isn't it nice when we repeat things in calculus? And that's what you're going to find when you get to Cal 3. We'll do the complete circuit and we'll basically be repeating the ideas of Cal 1, pulling all of that into 2 and 3 dimensions. And you'll find it to be a very elegant course because the foundations of the previous 2 courses will lift us to a level that gives us even more power as we do our computations. So now very easily here, we just replace x with a, and notice here we have a g of a minus a g of a and of f of a minus f of a. That clearly gives us 0. And then simply, if we replace x with b, pretty much the same thing, but notice here, the denominators absorb, the g of b minus g of a in this same term absorb. And we're left with what f of b minus f of b, which is 0, and then negative f of a minus a negative, which is plus f of a, which gives us 0. So we have the value of the function the same. That's necessarily going to guarantee the existence of at least one horizontal tangent. So now to finish the problem, it's very simple. By Rawls' theorem, there's a C between A and B such that H prime of C is 0. That is, we have a horizontal tangent, at least one. And so now we can just take the derivative and do what we need. Let's replace X with C and set that derivative equation equal to 0. And so when we do that, we have what? H prime of C minus the number, again, times G prime of C. So let's just transpose. Let's just take this over to the right-hand side. And now when we notice here, we're pretty much ready to go. We've got the number, that is the difference quotient, the values, differences of F and the differences of G. And then, of course, we can just divide by G prime of C, which we know is non-zero by hypothesis. So therefore, F prime of C divided by G prime of C is just f of b minus f of a divided by g of b minus g of a. So this is a very simple proof. And what I said before, go back and remind yourself of the proof of the mean value theorem. It's exactly the same. The function is just a little different, only to incorporate the function g. So it is a useful extension. Now, here's the theorem that we're going to use, and I don't think you will be surprised by this. This is one version, and of course in the lecture notes, there is a more detailed representation of the theorem and some more arithmetic, which you certainly should look through if there is an interest there. The main thing is that we are comfortable with this result when we are considering the condition 0 over 0. And then the arithmetic for infinity over infinity is not too terribly difficult, but it's good to start with this result. So what's going on? Okay, well, what's L'Hopital telling us? We suppose f and g are differentiable on the open set AB, except possibly at C. This sounds like we're just doing a limit. You know, we don't really know what's going on at C, but we want to know what's going on as close to C as we can. Maybe from either side, maybe it's a right limit or a left limit or a standard limit, whatever the case may be. Now, what we want to do, and you're thinking, how do we verify indeterminacy? Well, it's just that substitution method. When you're working with limits in calculus 1, you're thinking if you've got continuity at C, it's just mere substitution. But when you do the substitution and you end up with an infinite limit, which is again something different, a vertical asymptote, or you have the 0 over 0 or infinity over infinity, that's clear. You're thinking, well, I can't make a determination based on that analysis. So you simply verify that you have the 0 over 0. And also, this will be applicable to the infinity over infinity, or any combination plus or minus of that. We don't have to worry about the plus or minus. The function becomes unbounded in a sense that we're like, it's unbounded possibly. We just don't know what's going on. So with the infinite limit, we definitely have unbounded. Here we have even worse possibly, because we can't even say we have a vertical asymptote. So just remember, we often have students who are perplexed by this. Either of these two hypotheses will be sufficient to apply L'Hopital's rule. So if we have this is when we can say by L'Hopital that we can now move to a new limit. That is, we take the derivative of f and we take the derivative of g. Notice here, these are separate derivatives. This is not the derivative of a quotient. This is simply the derivative of f divided by the derivative of g. So make sure you have that down. That is critical. You're not doing a quotient rule, so please don't even think that way. You're taking ratios of derivatives. And then you look at this and you apply the limiting process. If you have a well-defined limit, you're done. Now, students will say, okay, well, I checked it again, it's still indeterminate. Okay, well, then you apply L'Hopital's rule again. So what's important here is that this is iterative. When you apply the rule and you get a limit, well-defined limit, just like you're working in calculus 1, then you're done. Okay, if not, maybe you have the hypothesis satisfied again. Then you apply the rule again. So you keep working until either you have a limit or maybe you get infinity. Who knows? The process is finite, but you can apply it as long as the hypotheses are satisfied. So as students tend to say about L'Hopital's rule, it is very, very user-friendly. Now, what I want to suggest here is that if we were working with unbounded functions with vertical asymptotes, we would actually consider this problem from the right or the left. So what we can do if we're considering the 0 over 0 case is we can just consider the approach of C from the right, so we can focus our arithmetic as we approach C to the right of C, from the right of C, that is. So again, using continuity, since we have differentiable functions, we would know that as x approaches C from the right, for f and g, we get 0. So this is what makes this particular proof very simple. And you see these applications, I finally got this in a form that I think will be easy to understand. And this is a two functions defined in pieces that the author of our text recommended, and I think it's quite ingenious. So what we can do, if we're approaching C from the right, we can just take some interval B, C to B, where B is to the right of C, and then make these definitions. That is, big F will just be f of x when x is between C and B, and then of course it will be 0 when x is equal to C, based upon our limit calculation. And we'll do the same for G. That is, big G will be G of x, where x is between C and B, and then 0 when x is equal to C. So again, the continuity and the differentiability follow for big F and big G because of the continuity and differentiability for F and G. So we're set up for the theorem. Now, one thing that's interesting about all of this is that we can directly apply the extended mean value theorem here. Notice, and as I've written here, kind of pedestrian-like, we just have the alpha between C and X here. So again, then as I've noticed here, F and G continuous on the interval C to X, where X is less than B, and differentiable on the interval C to X. So this is just simply providing a way to construct the limit. So we're going to let X approach C from the right. So this is, again, just an additional variable for user-friendly use, so to speak. So now we can first say, what does this say? F of X minus F of C, G of X minus G of C, when we're all talking about the uppercase letters. So by definition, again, we just apply the definitions. F of C and G of C are both 0, so we just have big F over big G. And now by definition, we go again, we're not equal to C, we're to the right of C, so we can replace big F with little f and big G with little g by definition. And then, of course, extended mean value theorem. Okay, so now we can replace, if you like, the derivative of big F and the derivative of big G by extended mean value theorem. So we're actually funneling back to here and going this way. But now what's interesting is that the derivative of big F and the derivative of big G are both F prime and G prime with the lowercase letters. So we back up to here to have the equality here from the extended mean value theorem, but then by definition of these functions in pieces, which is rather ingenious, gives us the mechanism to get to the lowercase letters. So I thought this was a very nice use of functions in pieces to set up this argument. Very, very clever. So now let's just see, what's the limit as x approaches C from the right of f of x over g of x? So now we can just think of a varying alpha. So if x is approaching C from the right, alpha will approach C from the right. So we can just make a change of variable here. And then, of course, we have the equality here. That is, we can replace f with f prime, and we can replace g with g prime and get an equality of the ratios. So we're using what we have right here from the extended mean value theorem to write this. And then, of course, same old song and dance. If alpha is approaching C from the right, we can also squeeze down on C by letting X do the same thing. So again, a reminder of the fundamental theorem of calculus. So again, what we see here is that as we approach C from the right, F over G, we actually get the same limit as we approach C from the right, F prime over G prime. So this is a very straightforward, user-friendly way of justifying the theorem for the 0 over 0. The arithmetic for the infinity over infinity is a little bit more complex, but it is actually doable. But I think what I want you to do is look at this and understand this method in its simplicity and also in its elegance. It's not simple, but what I tried to do is write this in a way so that it's easy to see when we apply the extended mean value theorem. So that's a very nice result and a very elegant argument. Now, what I wanted to do is just show you some examples that I have here. These are some additional notes that I have that showcase some techniques that you used in Cal 1. And then see if, just like doing the Weierstrass substitution, let's just say, okay, well, let's apply the new result. Let's apply L'Hopital's rule and see what we get. So what I have here is the first method. Let's just look at this. We're taking the limit as x approaches -1, okay? And when we look at this, we're thinking, okay, we're in Cal 1, do we have continuity? Well, let's check. Notice if x is approaching -1, the denominator is approaching 0. And then, of course, the square root here is approaching what? 1. So we have 1 minus 1. So when we look at this, we have the indeterminate. Sometimes I put this in quotes, basically as a form of indeterminacy. You don't need the quotes if you don't want, but I'll just say indeterminate. This does not give us an answer. You know, when you look at symbols to have arithmetic meaning, you must remember the rules. 0 over 0 is indeterminate. It's not 1. You don't know that. You cannot make that conclusion. Again, the indeterminate form is what we're interested in. So if we're in Calculus 1, we're thinking conjugate form. So let's just remind ourselves what we did. So we would take the conjugate of 1 minus square root of x plus 2 and do the plus. So we have 1 plus the square root of x plus 2 divided by 1 plus the square root of x plus 2. Okay, of course, now you've got a difference of squares, so you're just left with 1 minus x plus 2. And then downstairs, as I call it, you just got the riffraff. That is, you have x plus 1 times the quantity 1 plus the square root of x plus 2. And you just leave that alone. There's no need to simplify that or multiply it out. That would be a complete waste of time. So now when you look at this and you distribute, you have negative x plus 1 minus 2. So now what we see is we've got what? Negative x minus 1. Well, that's good. So what do? You factor. You see now that these two terms absorb. So now you've got the negative of the limit as x approaches -1 of 1 plus 1 divided by the square root of x plus 2. And then you're thinking, do I have a limit there? Absolutely. This is what we call the replacement theorem. It's like, okay, this is a function with a whole limit. So you're thinking, all right, the algebra is showing me an equivalent function as long as I stay away from -1. These are equivalent functions. So when you do this and you just simply replace x with -1 as if you are assuming continuity, you just get 1 divided by 1 plus 1 with a negative sign or -1/2. That was the method from Cal 1. There's no reason why you cannot continue to do that. But what we're going to find is you do transform methods in your differential equations classes, it will be very useful to have L'Hopital's rule because you won't have the mechanism of the algebra. Maybe you're dealing with the ratio of a polynomial to exponential functions, and you don't have the luxury of that beautiful algebra. So the L'Hopital's rule will be extremely useful, especially when you do Laplace transform. So just keep this in mind. This will be an extra tool. Now, what I want to do is just show you the second method. So we're back to the problem that we just did by the methods of Calculus 1. So when we look at that, we're thinking, okay, well, before we had indeterminate. I mean, just like it was before, there's no change in that. And we're thinking, okay, well, what students say, and they have to start thinking this way, well, I can take the derivative of that. Do I have to think about the interval? Again, what we're doing is we're thinking about an interval about -1, okay? And so we're thinking, do we have a well-defined function there? In some cases, we can't go too far away. We have to have a more restricted interval. But you look at this and say, okay, if I stay close enough to -1, I'm fine with the radical. Just don't get too far from -1. You'll be fine. So I do want you to think about that, but I don't want you to be paralyzed by thinking, oh my goodness, the hypotheses aren't here. I'm not going to try to set you up with that. Right now, I want you to get comfortable with utilizing this result. So just kind of do some basic ideas saying, as long as we stay close enough to -1, the square root of x plus 2 will make sense. So when we have the indeterminate form, we can apply L'Hopital, which says, now take the derivative. Okay, remember, we take the derivative of the function in the numerator, the derivative of the function in the denominator. And we can mix and match as long as we still have the 0/0. That's really important. You can move constants around and move them out or whatever, but you still have to make sure you've got that same indeterminate form. So now, of course, we can just apply calculus from calculus 1. So using the chain rule, the 1 is 0, of course, and we'll have a -1/2 times x plus 2 to the -1/2. And of course, the derivative of the denominator is 1. Now, we're back in Cal 1, so we just want to dress this up a little bit. Notice the -1/2 just kind of hangs out. So here you can factor it, and it can just become a coefficient, and you can bring the x plus 2 square root downstairs. Now, of course, this function is continuous there. This is not a surprise. We should get the same answer as we got before. And now just by continuity, you can do this limit based upon the techniques you learned before. So when you use L'Hopital's rule, you're still using the techniques of calculus 1. It's just that the L'Hopital's rule gets the ball rolling. And again, you keep applying it as long as it's valid to do so until you stop and say, okay, I've got a limit, or there is no limit. So just remember, L'Hopital's rule doesn't say there is a limit. It just simply says that if you're looking for one, you can look at f prime over g prime, or you can apply it again, another derivative over another derivative. And if you get a well-defined real number, then you're done. You have the limit of the original expression. So just remember, L'Hopital's rule does not guarantee the existence of a limit. It simply gives you a method of determining it that moves beyond the original expression. So of course, we get the -1/2 as we got before. Now one thing that you'll find in many examples is that if there's a feeling of saying, okay, I like my calculus 1 techniques, I'm not going to run away from them. Let me give you an example here. Some of these are very simple, but I want to focus on this one here. Notice we have x approaching 0 from the right, and we have e to the x minus the quantity 1 plus x, and then we have x cubed. Now, here's what's interesting about this, and I don't want you to look at this and think, okay, does it work? Does it not work? Whatever. Notice as x approaches 0 here, x cubed is clearly getting close to 0. And then, of course, x plus 1 is getting close to 1. And of course, e to the x is getting close to 1. So we do have 0/0. That's indeterminate form as long as we stay pretty close to 0 from the right. Now, so we can apply L'Hopital. Let's take derivatives. So we have the derivative here of -x, which is -1. E to the x is its own derivative. And then we can just utilize the power rule here. Now, again, we look at this again and let x approach 0. Does this make sense? Well, the same thing. In the numerator, we get close to 0, so to speak. We get the 0 that we're looking for. And then, of course, if we replace x with 0 here, we get the indeterminate. So we do it again. I'll just go ahead and write this in. We now have indeterminate again. So this is a case where you just keep applying the result. Or if you have infinity over infinity, same thing. So now we apply L'Hopital again. The derivative in the numerator is e to the x, and the derivative in the denominator is 6x. Now, when you look at this, you're thinking, oh, and notice what I've written here in red. X is approaching 0, but the numerator is not. So then I've written here definition of infinite limit, not indeterminate definition of vertical asymptote. But that's exactly what you learned about infinite limits in Cal 1. So you get to the point to where the denominator approaches 0, but the numerator is non-zero. So that's an indication where the function will become unbounded. And then, of course, the problem is arithmetic. So you're thinking as we approach x or 0 from the right, the denominator is clearly positive and the numerator is positive. So this sets up the unbounded nature or positive infinity. So what's important here is the application of L'Hopital's rule until we get to a point where we can no longer apply L'Hopital's rule. Can we make a conclusion? And then that takes you right back to calculus 1. So using L'Hopital's rule is going to make you better at computing limits, because now you have an additional tool, but then you have to remember the ideas that you learned in your previous course. Now, what I want to do is show you another example of a problem that, again, just like before, we can use an old technique. So notice here, and I've done this kind of 2 different ways, but I'll focus on this one. You can use this as you want. But here's the function, the limit right here. That is, we have the limit as x approaches infinity of x squared divided by the square root of x squared plus 1. So L'Hopital's rule is very flexible. Notice I didn't state this explicitly in our theorem. We can also look at limits at infinity, okay, as x is becoming arbitrarily large or infinitesimally small. If we still get the 0 over 0 or the infinity over infinity, arithmetically, we can recast that as a L'Hopital's hypothesis. So what we see is that we can still apply the conclusion and say, okay, now look at this particular function where we've got a ratio of derivatives. Now, before we do that, let's just look at this and notice, if you will, as x approaches infinity, this is just infinity over infinity. And so you're thinking, how would we do this in Cal 1? Well, I've got 2 setups here. You can use the first setup, which would clearly be infinite, and then I just did some estimations here. But the easiest way to look at it is just to rewrite x squared as the square root of x to the 4th, and then take the numerator and denominator under the umbrella, so to speak. And then you're like, okay, well, let's factor the x squared out of the numerator and denominator. These clearly absorb. So just the same song and dance, nothing new, very simple. And then you look at this and say, okay, well, let's use continuity. You know, as we run out to infinity, the square root function is certainly defined, so we can run the limit inside. And so now, of course, as x passes to infinity, the denominator approaches 1 because 1 over x squared gets very close to 0. And of course, the numerator just becomes unbounded. So this is what we call a infinite limit at infinity. Again, another calculus result. I mean, we did infinite limits where we have vertical asymptotes, and then we have limits at infinity. Well, limits at infinity are just basically looking at sequences. When you do sequences, you're like, oh yeah, that's a limit at infinity, and we're just restricting to natural numbers. We get all of that beautiful calculus that gets transferred to sequences. So we're very fortunate when we're in calculus 2 because we have all the foundation from Cal 1. So when you do this in a rigorous fashion, you're like, oh wow, look at what we can do. Okay, well, what would we do with this problem if we didn't use that technique? And you're going to look at the alternative and think this is just really simple. So if we go back to the original problem, we have the limit as we have what? X squared divided by the square root of x squared plus 1. Well, again, this is indeterminate. Okay, so if we apply L'Hopital's rule, which says now we can look at the limit of the numerator derivative divided by the denominator derivative, or f prime over g prime, whatever you want to call it. And so now when we take the derivative of x squared, we get 2x. And then, of course, if we look at the denominator, we apply the chain rule. So we just have 1/2 times x squared plus 1 to the negative 1/2. This is really easy. We did some really difficult derivatives and optimization problems in Cal 1 that really taxed us. At least here, this is straightforward and gives you a break. But notice the two x terms absorb, and you're just left with, well, you just kind of bring this upstairs. The reciprocal of 1/2 is 2. And now you just have the square root of x squared plus 1, and x is tended to infinity. Well, again, that's an infinite limit at infinity. We get the same result, which of course we expect. You know, just like doing the problem with the rational expressions of sine and cosine to the first degree, of course, we're going to get a valid response if we're applying a legitimate technique. Like I said before, you may not find that you need to think about L'Hopital's rule, especially if you have an alternative. If you're thinking, and here's another example. Remember, we did lots of work for this particular problem. We used the squeeze theorem and all kinds of arithmetic to get the result of 1. Okay, and you'll see these in the notes. Well, if you look at this, if x is approaching 0, we do get the 0 over 0 in determinate form. So if you wanted to apply L'Hopital, you could. So you have the limit as x approaches 0, the derivative of sine is cosine, and the derivative of x is 1. But of course, this is just a simple limit. This is continuous. Cosine of 0 is clearly 1. Well, of course, that is trivial compared to all of the work that we had to do to prove that. I mean, but that is the essence of Calculus 1, understanding the arithmetic of the limit. If I just said, oh, we'll just go ahead and use this result, then you would have gotten no information about how the process of limits works. You think about epsilon delta definition, you think about the squeeze theorem, you think that when it's simple, fine. But when it's not simple, you have to use a more complicated approach. So it was important that I taught you that. Now you can look at this and say, wow, with L'Hopital's rule, this is quick. But then go back to your notes in Calculus 1 and study how you basically derive the limit for this using other means. Now, of course, you know this limit because you've used it so much, and manifestations of it you've done many times. So now that you have this additional tool, you can say, well, even if I forgot this, I can quickly get the answer using L'Hopital's theorem. So we'll take it. Now, one thing that I think is interesting is we have this one form that I gave you on the first page. For instance, we could have 1 to the infinity, infinity minus infinity. Any of these, what we would want to do is try to convert them to either 0 over 0 or infinity over infinity. So let's look at an example of where we use continuity here. And I tried to reframe this in terms of the notation that we've used in our previous courses. Notice this problem's not going to make sense unless we're approaching x through positive numbers. And of course, if I write just x approaching 0, the tacit assumption is that we are working with real value functions. So I just did a little example here showing you that, of course, if we're less than 0, the function argument is negative. And then, of course, if we're taking square roots or even nth roots of that, it's not real. So we have to stick with this. So just keep that in mind when you're doing this. Now, the problem is phrased this way from your homework. It says compute C so that the function is continuous at C. So what we would need, and what's important here, is that when we take the limit as, in this case, x approaches 0 from the right, we would want to be able to get what? C. I mean, by continuity, let's just write that down. I'll use the blue. So the goal would be the limit as x approaches 0 from the right of f of x would just need to be c. That is f of 0, which is c. So this is the continuity result from Cal 1. We'll say continuity at 0. So if we're approaching 0 from the right and f is continuous there, this should be f of 0, but by definition, f of 0 is c. So it's important to state it in context of this. So what I've done here is compute c so that the function is actually continuous at 0. So this is, it's like, well, okay, so what's C? We're calling it C, but can we do better than that? Well, of course we have to do better than that because we've got to have a well-defined real number. This C is just a placeholder, but this is an easy problem if we think about L'Hopital's rule. Now, what I've done here is I've written this in a form that makes sense, at least in terms of limits. So in order to use continuity of the logarithm, what we do is we just set y, use any variable you want, to be the limit as x approaches 0 from the right of f, which is e to the x plus 8x to the 1 over x. So this is the key here. This is the key step right here. So now, when we do that, we're thinking, all right, well, we've got the indeterminate form. Let's just check on this. As x approaches 0 from the right, we basically have 1 to the 1 over x, and that's just infinity. So we have 1 to the infinity, which is an indeterminate form. So we're thinking that's not going to be something to which we can apply L'Hopital's rule. Well, the trick is to make this definition and then apply the natural logarithm, because these are positive values. So now we look at the natural logarithm of y, which would be the log of this limit. Okay, so again, the easiest way to set up this problem is just to state the limit that you're computing and assign it a variable of your choice. Z, theta, omega, I use y, doesn't matter. And so now the log of y is this, but this is where I talked about continuity. That is, the logarithm is continuous for positive real numbers. So now that means that we can interchange the function and the limiting process. Again, continuity is very important here. Notice x is approaching 0 here. So basically, we run the limit inside. And what is the limit of x as x approaches 0? Well, it's 0. So we're basically stating this, even though I'm not writing that limit specifically here. When I write this, I have interchanged the limit in f. That is continuity. Unfortunately, this is usually the way it's written, and you kind of forget that when you're using that particular property. But continuity allows us to interchange the function and the limiting process. So you're thinking, I got you. So now when we do that, we interchange the log and the limiting process, and then we're thinking, great, power rule. So now the log of the power function, so to speak, the 1 over x can come down. So we have a coefficient of 1 over x, which allows us to move the x into the denominator. So just remember, the power rule, let me just write this out. We have log of e to the x plus 8x 1 over x. So now we can bring the power to the coefficient and write this. And then, of course, we can just move the x here into the denominator to write that. But now when you allow x to approach 0 from the right, we have the log of 1, which is 0, and x is approaching 0. So we definitely have the indeterminate form 0 over 0. So that's the key. This is what I was talking about. Even though this is a little bit more complicated, usually you can just use algebra to fix the problem. I mean, simple algebra. But here, when you're dealing with power functions, that is, you've got exponentials, you might have just algebraic power functions. You can always use the logarithm to bring the power to the coefficient, and then manufacture the indeterminate form, either 0 over 0 or infinity over infinity, which then would allow you to apply L'Hopital's rule. So that's the key here. This is an important example and something you will use many times as you continue in your mathematics study. So now we're good to go. And notice I keep doing LH for L'Hopital. That means I've applied the rule. So now when we take the derivative here using the log function, we take the reciprocal of the argument times the derivative of the argument, which is e to the x plus 8. And of course, the derivative of x is just 1. So now what are we left with? We have the limit as x approaches 0 of e to the x plus 8 divided by e to the x plus 8x. And of course, now we can just use continuity. Replace x with 0, so we get 1 plus 8, and then we just get 1 plus 0. So the limit is indeed 9, at least for the log of y. And what's a logarithm? Power of the base. So now we just apply that. So y would just be e to the 9. The power of, in this particular case, of e that gives us the required value of c is 9. So we now know that we need the value e to the 9 to go here for the function to be continuous. So again, we figured out that the limit of f as x approaches 0 here, and then we just simply apply the definition of logarithm. And so this e to the 9 can go in for c here, and we know we have continuity at 0. So again, we get this. Now we can replace the c with this number. And let me move this up, pointing at something you can't see, e to the 9. So take this example as a very useful strategy for taking power functions and reclaiming them using the what? Natural logarithm to rewrite them to satisfy the indeterminate form. Again, this is such a popular technique. You will see this many, many times over. And if you go back to your college algebra, when you're talking about compound interest and also continuous interest, you can see all of this going on. You see, as you make the transition to continuous interest, the base e just magically appears. Well, this is what's going on here. So now you can go back to those lessons and actually understand possibly what was going on. So do spend some time with this example. I think it will be very useful to you. Now, one other example that I want to talk about, again, you don't ever feel afraid to look at anything algebraically. Manufacture the 0 over 0 or infinity over infinity utilizing legitimate mathematics. It's not hard to do. As long as you abide by the algebra, you will be able to validly apply L'Hopital's rule. And I think you're going to enjoy it, and you're going to feel a sense of strength, especially when you get to physics and engineering. Now, again, you see I have a similar problem here utilizing the same technique, but I won't go through that. We just talked about one from your homework. What I want to talk about here, and I say excellent illustration, is I want to refer to one of the indeterminate forms that we had before. Like the last one, we have 1 to the infinity, so we have to manufacture 0 over 0. So here, let's just see why this would be a good candidate for, in this particular case, L'Hopital's rule. Notice X is approaching 2. I've done this diagrammatically here. Picture math, of course, that's not how we reason, but sometimes the diagram helps us to organize. So again, we're approaching 2 from the right. And what we can see in this particular case is that 2 is a vertical asymptote. It defines a vertical asymptote for this function and this function. But we're approaching from the right, and both of the functions have positive values. So that would mean an infinity minus an infinity. So this gives us an indeterminate form. So we look at this and say, yes, maybe we can manufacture the correct form to apply L'Hopital's rule. You're thinking, is the answer 0? Well, we certainly wouldn't know that because this is indeterminate. That is not conclusive. So what we can do, and this is what I was talking about utilizing algebra. So what we can do at this point is just, again, factor the x squared minus 4 is x minus 2 times x plus 2, and then get a common denominator. So again, we multiply the negative x times x plus 2 as we have here, just doing basic algebra 1. So now we have x minus x squared minus 2x. Now notice, and I just want to do a little bit more maneuvering here. If you look at this and write this in descending form, we have negative x squared minus 2x plus 8, and then we have x squared minus 4. Okay, well, here we had infinity minus infinity. Let's check it again. If we replace x with 2, notice here, this gives us a negative 4 minus a 4. That's a negative 8 plus 8. That gives us a 0. And clearly in the denominator, we have 4 minus 4. So we have the so-called indeterminate form, which we easily manufactured with very, very simple algebra. So nothing as complicated as using continuity of the natural logarithm. That won't be difficult once you practice a couple of examples and then teach it to someone. I think you'll find that to be the best way to become more adept at applying it. But now, of course, we're thinking, give us the polynomials. We can differentiate those all day. We found how nice that was when we had a polynomial factor in an integration by parts problem where we could simply differentiate that to 0 and, home free, right? So now we take the derivative here, we get a negative 2x minus a 2, and then a 2x. Now, of course, when we look at this, we're thinking, all right, well, let's just go ahead and, we work for the government, so we want our work to look nice. So we factor the negative 2, and the negative 2 and the 2 absorb, leaving us behind the negative 1. So now we just have the additive inverse of x plus 1 divided by x. But this is clearly continuous at 2. We just replace x with 2, we get negative 3/2. So what we see here is the L'Hopital's rule is not half bad. I mean, we think about this and then we're thinking, if we don't do the L'Hopital's rule, we can just factor this and absorb the factor that's getting in the way. This just simply provides a new avenue. Okay, so again, this problem did not require L'Hopital's rule, but I set it up for that. We didn't have to do additional factoring, which we could have done in a Calculus 1 course. But just like I said before, as you're doing different integration techniques, you still get a valid response. Don't push away techniques from the past and think, okay, L'Hopital's rule is now going to be the way to compute limits. It is a way, but it is certainly not something that is always applicable. So you still need the techniques from the past to have all the proper tools to do calculus effectively. So I hope that you have enjoyed learning about L'Hopital's rule and the extended mean value theorem. They're very simple, but very, very useful. So enjoy working through these examples. I think you'll find them a little bit easier than the more complicated integration techniques, and actually quite refreshing. And as I've remembered, students don't ever forget L'Hopital's rule. So when they see it again, they clearly remember it. Okay, and we are done.